AQUABIZ, all the best knowledge for aquatic system.
Thank you for inviting me to talk to you guys, and I will be interacting with you guys as much as you deliver this speech, but it's my own philosophy to interact with you guys. So I will present to you some of the experience that we have in Latin America. These experiences, it wasn't just from yesterday to today that came up to be at this stage. It took some time. It took some time to mature the idea, what is this technology, what it can do. And in the middle of that time also was COVID-19. So it's the same here. You guys have to mature the idea how this works and how we can make money with this technology. That's basically it. The investor have to be entitled to evaluate the technology to see if it works or not. And in Latin America, it took some time to evaluate those, especially with tilapia in the beginning, because we have data on other species, but the main culture species is tilapia. And once they have the numbers, you will see it in the next presentation. So let's start it. During COVID-19, we have the same problem. I see the same problem in Latin America and every country I visit in Southeast Asia. The prices of the feed staff and the operation system has been quite high, elevated, and the selling price has not matched at the same altitude. So it doesn't matter what country in Latin America, from Mexico to Peru, it was the same. And when I come to this country last year, we find out that it's the same problem. The prices do not match the operation cost, and the profits were very limited, and we find out with sources, especially from FAO, that they're coming back up. The selling prices are coming back up. Latin America just started last year. The prices are coming back up. So I hope so that very soon with you guys here, the selling prices start coming back, that the profits also more viable. So in this technology, we see in Latin America also coming back, producing more fish. Usually, you will see it in the next presentation, the slides, but usually Latin America is developing about 9 to 10% every year. It's producing more fish, and especially now that the selling price of fish is getting better, this is going in the right direction. So in the case of Colombia, for example, up to year 17, they produce around 130,000 tons, metric tons, which is not much by then. But every year is increasing about 9%. So what Colombia do is increasing about 9%, but they have some species, mainly tilapia, but there are some species that you have, or at least Vietnam and China already have it, but the main is tilapia. It's important to notice here that in Latin America, there are 3 different market size tilapia. One is family consumption, which is between 250 grams to 350 grams, a small tilapia. Why this market? Because a family can buy 1 pound or 1 kilo and feed a family. It's very desirable market size. The second market size is between 500 grams to 600 grams, which is a restaurant fish. And the third size is between 800 to 1,200 grams, which is the fillet size. So these three sizes are the ones that reign or direct the markets in Latin America. That means it doesn't matter what size fish you produce, if there is a market for it. The fillet is mostly produced to supply market in the United States. So Mexico is produced around 35,000 metric tons, and it's also growing at almost at the same rate that Colombia. Those are the main countries that produce fish in Latin America. Also Honduras, as you see in the presentation previous introduction with Regal Springs. In Costa Rica also there are businesses that produce fish, mostly commercial for export to the United States. So this is not a new slide. It's a year 16, I believe. But the important in here is why the Latin American countries producing tilapia are not rejected to import it into the United States. It's a new business in Latin America. And the processing plants are designed with the specifications of USDA and FDA. So everything is already match those specifications. And once you deliver those fishes to the United States, all sanitation, all security, everything pass with flying colors. So this is something that don't happen in here. There are some reactions, and you have to be careful with that, because you don't want your reaction to come, your reputation is in the line. You just be careful with that. So in this sense, where this technology came on board to light. We have a professor, Michael Masser, extension professor in Auburn University. He was a professor that was producing fish in cages, but he had the idea to say, why we don't build something to make the water go through the fish instead of just stuck the water in a cage. And he put air lifts, and basically this is very small, very about the size of this platform. Very rustic, basic idea. And use a blower and air lift system to make water going through the fish, but you see the sediments, very rustic, basic, empiric. So he publishes this information in the Regional Aquaculture Center number 170. And why we took this technology, Jesse Chappell in this case, why we took this technology and developed it a little bigger commercial size? Because of one single necessity. Vietnam started importing fish, pangasius fish, to the United States, and literally broke the production in catfish farmers of America in the United States. And the farmers came to Auburn University to ask for a solution, how we can compete with those guys in Vietnam. The production of pangasius in Vietnam is impossible to beat. It's impossible, not with catfish. So, but we put some solutions on it. We looked for solutions. And one of them was take this idea and convert it. Think about this. This is for the Model T4 in the 1930s. And we built, instead of this same car, we built a Ferrari or Lamborghini. Faster, more efficient, better roads, everything. And this is what is coming up, but this is the basic concept. So the other idea that we promote to the farmers in the United States was the catfish hybrid, which is incredible, better than the regular catfish. So, saying so, we took this idea and converted into what is today the IPRS. Basically, idea is you have your chickens in the yard, loosen in the yard, and then you put it in a chicken coops. Basically the same thing, where you have more control of the situation in this area, and you have the pond as the treatment plant, control of the water quality. But what is the best idea that came out of this thing? Remember, Jesse Chappell, my person, and Terry Hanson, we all retired from our university already. But the years that we have spent in educating ourselves and experience in the working labor in fish end up right here. So the best scenario here is that we convert this system into environmental friendly and educated. The heart of the system is this. Basically is the water mover the white water unit. Unfortunately, the video didn't run quite smooth, but what we're trying to show here is that the diffuser rack producing a lot of bubbles coming up, and that bubbles is deflected into the fish, and we achieve two things: aeration and moving water just with one blower. So put attention to that, because from one blower we move water and oxygenate at the same time. So when we build this thing, this white water unit, please use the aerotube hoses. Do not use the imitation. And this is why. Can we run this video one more time, please? This is the imitation, and this is aerotube, made in America. It's a big difference. If you build this system and adapt this system, and you use the imitation, you assume yourself you're meeting the specifications, and you're not. This is very important. So, because if you do not provide the enough velocity of water and enough oxygen into the fish, you are not doing the job. So, this is very important. So, what is the water velocity that we're shooting for? What is our goal? If you see here in this slide, there is a variety of velocity that we have, but in the overall, it's an average of 10 centimeters per second. This is what we're looking for. Of course, during the time that we have this running 24/7, there is biofouling into the hoses, and every harvest, you have to take it out, clean it back up, and put it into the system back. The cleaning and the maintenance is important to keep the same velocity all the time. If you do not clean it up, then you diminish the amount of oxygen and also diminish the velocity, which is critical for the system to sustain the amount of kilograms per cubic meter that we looking to harvest. Okay. This is the first system built in Latin America. After a conference like this, one of the participants, manager of a fish farm, went to his place just with the idea and started building this by himself, without any guidance, without any question, nothing, you just went up there. And eventually, the word come up to us, said, oh, this guy up there is building an IPRS. We call him, say, stop, please stop. less us helping you guys. Hold on. When we were to visit, we found this already halfway done, with some mistakes. Of course, there were mistakes, especially from this area here where the water movers will be and the pond bank. You will see it later on in the next. But what I want to show you here is that just build the walls and put a pond liner in the bottom, which is fairly economical way to do it. Because if you do it completely out of concrete, a little more expensive. And there are other ways also to make it more economical and continue to be efficient. So one of the features that we promoted in the beginning was the 3-meter quiescent zone or sedimentation zone in 3 meters from here to here. But later on, we realized that 6 meters is better. Remember, this area here make this technology environmental friendly. You will see it later on. But it's highly important. If you take the fish waste out of the water, question for you guys. What technology take the fish waste out of the water, out of the aquatic environment? As far as I know, RAS is the only one. Correct? Okay. But in the open ponds, can you do that? Huh? Think about it. It's impossible. Impossible. But this technology do. And this is part of why we can produce a lot of fish in the same water over and over for years. Because if you take the fish waste out of the water is what pollute the water, deteriorate the water over time. And you end up having harvest and dumping that water into the waterways, into rivers, lagoons, and end up in the ocean. So we are the contributors. I mean, I'm sorry to say so, blindly, but we contribute to the pollution of our environment. It's a reality. I'm sorry, but it's a fact. Now, this technology is not polluting. We're taking the fish waste out of the aquatic environment. And that's the beauty of that. Think about government regulations. What happened in China, the example of China, years back. The government said you do not dump water out of the traditional ponds into the ecosystems. Oh, what we do now? That's what this technology took over down there because of the environmental friendly that it is. So, we continue in the first stage of our development of this technology. We continue with the 3 meters, but again, later on we realized that 6 meters is a lot better. We take a lot more fish waste out of the water. So basically, this makes this technology environmental friendly. No question about it. And I will present you some facts. So like this one, we know for a fact that in trout, I want you to check in this number right here and this number, just keep it in your memory when we discuss this, what coming out of the fish waste out of the water as a fertilizer. Just keep the number in mind, because we will discuss this later on. What I want you to do is the feed intake out of this one, the fish waste in the intake is about, overall picture in trout, 79%. What is in the meat of the fish? What is in the body of the fish? It's not much. Everything else is just going through the digestion system into the water. That's the importance of this number right here. So we continue with the fish extractor. This is in Mexico. We continue. This is the first stages in our development in 3 meters. And also in China, in the beginning, we were thinking that it was enough, but it's not. So, and then we start working in 6 meters in Vietnam. incredible. It's outstanding. Outstanding. Just look at the color, what is coming out of there. Now, what we do with it? Think about it. Once we get it out of the water, what we do with it? What is in there? How much is it? What is the value? So, this is in Colombia. This is 6 meters already. But I want you to take one more shot at Vietnam. This one is 2 inches pipe. A small motor, a small pump, more efficient, less consumption of energy. These don't run every day, all day long. This is about 4, 5, 6, 7 times a day only. Sweep back and forth and stop. There's not much energy there, but the cost is building the 2 units, taking fish waste out of the water. So, look at the 2 inches compared with Colombia. They're talking about 4 inches with a massive pump, costly, massive pump. And in here, they have a variable speed device that decrease the hertz in the motor and is adjusting the velocity of the pump until they get to the point where exactly no spill of this material into the water. So you will see it in a minute. It's going down, 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 and there you have it. So why we put a big pump and we have to reduce the revolutions? That don't make sense, but they like to big things. So no problem there. If we take the fish waste out of the water, it's good. We are doing outstandingly well. So basically, in the channel of the discharge channel, we end up in this area here. This area here overflow to the second one, and the second one overflow in the third one, and the water come back to the pond. That's why we save water. But in this area here, we put plants. This is very a small, early stage of, what is the name? Can help me with that number? The name? Aquatic? Water hyacinth. They had a violet flower. So this is very early stages. But basically, that plant, it doesn't matter how concentrated is the nutrients there. It don't mind. It take all the nitrogen out and convert it into plant, and the water run into the system here and come back with less nitrogen that came in. That's the overall picture that we have. So we come back to say that 6 meters is a lot better, by no question. And this is another one at 6 meters. So it's working really well, collecting the fish waste, taking it out of the water. But what we do with it? How much is coming out? Now, let's stop here before we analyze what we have here, and we have to say that out of the 79, somewhere in that neighborhood of feed that coming through the fish, what is coming out of the fish? There are 3 components. One is in solution. Basically, you cannot collect that by no means into the water. The second are colloids. And the third one are the solids. But the solids are also converted into coarse, medium size, and fines. What we can collect out of that is only the coarse grain and some of the medium size. But the question here is, well, we have been saying all along, well, yeah, we can use this as a fertilizer. And last year, I ran an experiment in Honduras, trying to quantify and characterize the tilapia westerly collection. What is it? How much is coming out? And in my literature review, it came out to be that the number that I asked you to put in memory in trout, 7 of nitrogen and so forth in potassium, I couldn't find any in tilapia. Only one single author, which is David Birch in Auburn University, was taking samples out of a biofloc tank and analyze it in the lab to see how much is coming, what minerals and nutrients is coming out of there. That's the only paper I found. So in this case, we run 8 small raceways, floating raceways, in an experiment in 2 diets. 4 for one diet and 4 to the second diet. So, and we took many samples every 15 days. This is not just one sample. It's a statistical proof that is absolutely different between one diet and another one. And this is what we find out. If the feed intake is in dry matter, as the feed is, about 10, 11% of moisture, what is the comparison in percent of fecal material coming out of there? And we find out that the diet B went up to 8.22%. That's the highest that we have. I mean, compare 8% as maximum coming out of there after you feed. It's not much, eh? Really, it's not much you're taking out. And in the diet A, I mean, diet A is not much. The highest was 2.14%. It's not much. Now, look at the other one. Look at here. This is significant. Because if we analyze diet A, diet B, of course we have a range. But the average of that range, let's call for nitrogen. It's coming at 0.58 and 0.75. But look at this column. This is coming out of Zamorano University in Honduras. It's a highly prestigious university. It's basically an American university in Honduras with those standards. And those guys recommend that for nitrogen, most of the agriculture crop required between 0.10 to 0.20, and how much we have? 0.75 in diet B, and diet A, 0.58. Almost 3 or more times in nitrogen. But take a look of phosphorus and potassium. Phosphorus, 3,000, 2,300. And it's only required 13 to 30. Look at the value. Look what we got there. This is a gold mine. Even though we got very little out of there, but it's highly valuable. Potassium, more than 3,000, almost 3,000, and it's only required 150 and 280. What about that? Huh, interesting, eh? Doesn't mean, oh, okay, we got more minerals and calcium and magnesium and so forth. And then there is some more other ones that I didn't put in here. This is probably the most important ones. But let me ask you guys a question. We cannot put this highly nutrient into the row crops because we burn the row crop. We kill it. They have to be diluted. The following research have to be with the agriculture engineers to find out how much we can put in there, how we dilute this material, and hey, you add value to this? how much we can sell out of that. Huh? If you collect that and you get another income for the farm, what about that? Now, do we have in the house a nutritionist, a feed nutritionist? I believe so. Well, I want to ask you the following question. Check what is in yellow, color yellow. What element is in there? Sodium. Ooh, we have a problem. We have a problem because required for row crops less than 230. And look how much it is. We cannot use it that way. Absolutely not. I mean, some of you guys know what the effect of sodium do in a row crop? Somebody? Well, I give it you as a homework. Okay. So, nutritionist, where did sodium come from? Any idea?
Mainly from salt, right?
Come back?
Mainly from salt, coming from ingredients, and also the extraction from excretion from the animal.
Okay, thank you. Good information. But also want to emphasize here, in Latin America, especially in Central America, they use salt to treat parasites in the fish. And I mean, tilapia is very well known from trichodina. And trichodina, you treat with salt, it diminishes the population and the fish get better helped. That's another source. But independently of the treatment of salt in fish, I have another literature review in United States that also claim high content of sodium, which they do not treat with salt. Where that come from then? Thank you for your answer. So, because I also asked the same question to other nutritionists or formulators in Latin America with feed formulations. And they say sometimes they use salt as a filler in feed stuff. Ooh, that's news. Now, question here. Can we get rid of this? Yes. If we don't treat the fish with salt, we eliminate most of it automatically out. If we ask the formulator to not put any salt in there, we take it out. Can we go down to this number? I think so. Very easy. I don't see much of a problem once we know what we have. So, then, if we take this out of the equation, this is a golden mine. Not just for the actual add value, but how much are we getting out of the aquatic environment? That's what this technology makes it outstandingly environmental friendly. The second one is how much time can you use the same water. Our experiments run for sometimes up to 7 years to use the same water, just replacing basically what is evaporating and some seepage in the soil, in the ground. So, saying so, in the following section will be answered some of these questions that everybody is asking themselves. Why I or my company will be adopting this technology? Difference between traditional ponds and IPRS production. How how many years I recover my investment? Those are the questions, common questions that everybody thinking about adapting this technology will ask. Some of the questions is, if I run the blowers 24/7, my electric bill will be high. Yes, it is, but the production is also high. So we will evaluate those questions in more specific ways. So, is this technology safe water? And more questions that you guys have in mind that I would like to see what you got, and we can answer them. So, do we stop here? Okay. Let's take a break. Let's get some snacks, and we come back after the break. Okay?